Hello. In the last video, we were able to talk about capacitor, capacitance, and many other things. Um, in today's class, we are going to be talking about capacitors in parallel. But before we go into that, let's still do a refresher. Okay, in the last video, we've been able to establish the fact that Q is equal to CV, and we said that C is equal to Q over V. Okay, now I want you to know that another formula for C is what? EA over D. EA over D, where E is what? Permittivity of the material. Okay, permittivity of the material, and the unit is FM per meter, and A is the area of overlap of the plate and is measured in meter square. D is the distance between the plate and is measured in what? Meter. Okay, that's by the way. Let's talk about capacitors in parallel. Now, if we have capacitors in parallel arranged as shown on the board, the following applies. Okay, follow me. Then we have one. This number one applies when a capacitor is arranged in parallel. So we have one, the equivalent capacitor, or the total capacitor, or the net capacitor, or the combined capacitor is given as C is equal to C1 plus C2 plus what? C3. Number two. Okay, now for this capacitor, capacitor 1, capacitor 2, capacitor 3, for C1, C2, C3, they all have the same potential difference. So the same, another thing you need to know is that they have the same potential difference, V. Number 3, the total circuit charge. The total, you can see that the charge is not the same. We have Q1, Q2, Q3. The total cycle charge. So we have the total cycle charge Q will be equal to Q1 plus Q2 plus Q3. Okay, so it means, in case you are not given Q1, Q2, Q3, you should find Q1, Q2, Q3, and then sum to find total cycle charge. So now what will be the formula to find Q1? The formula will be this. From here. Okay? So if you Q1 will be what? Equal to what? Q will not be equal, Q1 will be equal to what? From here. It will be what? C1V. Q2 will be equal to what? C2V. And Q3 will be equal to what? C3V. Okay, are you surprised that you're having VVV, not V1, V2, V3? Do you still remember rule number 2? That's what? The potential difference is the same. Okay, when capacitors are arranged in parallel, the potential difference is the same for all capacitors. Even if they are 10, the potential difference is the same. Is that okay? Now let's talk about capacitance in series. You should know that capacitance in parallel is like you are arranging them on top of each other. That's in parallel, on top of each other. Okay. Now, when it comes to series, it is end to end, like on a straight line. You are arranging them end to end on a straight line. But parallel is on top of each other, like that. So let me draw for series. Now, for series, this is what we will have. It's going to be this way. Can you see what I've said? It is what? End to end. End to end. So we have Q, 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 Q. Of course, this side will be negative, negative, and the other side will be what? Positive, positive. Okay, and we have C, and then we have let me just draw it a straight line. So let's say this is where we joined them together. Okay, let's just say this is where it was joined together. So we have from here to here as our V1, from this end to this end where it was joined V2, from this end to this end we have our V3. Are you seeing? So now let's see what is applicable to capacitors in series. Capacitors in series. Let's see what is applicable to this. Now, for the first application, I'm not going to wipe. As I'm solving this, I'll wipe the old information so that it will make sense. Okay. Now, for capacitors in series, the equivalent, the total, the combined capacitor, okay, is the opposite of this one. Okay. Now, this is how it's going to look like. Okay. It's going to be 1 over C1 plus, 1 over C. 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Can you say this? Okay, now the second application. What is applicable? The second rule for capacitors in series. When we talked about for parallel, we said they all have the same potential difference. Now for series, they don't have the same potential difference, but they have the same charge. They have the same charge. They have the same charge Q. Are you following? Now, when it comes to the total cycled voltage, you can see when we talked about the parallel, it is the charge that is different. The charge is different. But when it comes to series, is the voltage that is different. You can see it here, V1, V2, V3. So the total cycled voltage, so we're not going to be talking about the total cycled charge in this case, since they have the same charge. So the total cycled voltage is going to be what? V is equal to V1 plus V2 plus V3. Are you following? So now, from here, if we make V the subject of it means we'll have V is equal to what? Q over C. Okay? So from here, we can find V1. V1 will be equal to what? It's going to be equal to Q all over C1, right? V2 will be equal to, because they have the same charge, so we're not going to number the charge. We have Q2 is equal to what? We're not numbering charge. All over C2. Then V3 will be equal to what? Q all over what? C3. And this is the application, whatever applies to what? Capacitors in series. You can see the arrangement is what? End to end. End to end. But for parallel is on top of what? Each other. Okay? So, and that is that for capacitors in series. I hope you enjoyed today's lesson. I'm still Bukola Joseph, the physics enthusiast. We will be applying all that we have learned in the teaching of capacitors, capacitors in series, capacitors in parallel. Bye.